section 8.6 today. And we're going to talk about area and volume proportions. So far, like I said before, so far what we've been talking about is comparing the side lengths of similar figures. And what we want to talk about now is if we have similar figures, some kind of shape, if they're similar, how do their volumes compare? What do we know about their volumes? And if we have a 3D shape, if they're similar, with flat shapes, with 2D figures, we want to figure out how their area compares. And if they're 3D shapes, we want to figure out how their volumes compare. So if we know they're similar, how do we compare their volumes? How do we compare their areas? So we have a couple of rules that we can use. So we have, if we know two similar figures, so we know our figures are similar. We figured it out somehow. The problem tells us somehow we know that our figures are similar. And we know that the length ratio and by length ratio I mean a side, a diameter, a circumference, a height, any kind of length. If they have a length ratio of A over B, some fraction, if we know that the length ratio is A over B, they have the area ratio A squared over B squared. So what we're saying is we square the length ratio to get the area ratio. So on our opener, we knew the ratio of figure out the ratio of the sides of the triangles. We could figure out the ratio of the areas of the triangles. That's what this rule lets us do. And we can think of it, if we think of our units for length and area, we know that length has units, just units, inches, meters, whatever. And area has units, square inches, square yards, square miles, something. So to go from length to area, we have to square. To go from a length ratio to an area ratio, we square it. And any length ratio in our similar figure is going to be A over B. So we know the side ratio is A over B. The ratio of the heights is going to be A over B. The ratio of the perimeter is going to be A over B. Any length ratio is going to be the same. And we square that to get the area ratio. So any questions about what this rule is telling us? All right, let's look at a couple of examples using this. So for this example, we have a triangle, and we're going to divide it up. We've been looking at lots of pictures like these in this chapter. And we'll label the points like so. And we'll say that this is 4 and this is 5. And we want to find the ratio of the areas of triangle ABC. and triangle ADE. So we're comparing the small triangle here to the big triangle there. Well, we know that the triangles, these two triangles are similar. These two sides are parallel, so that tells us it divides the sides proportionally. They share this vertex angle, so we know that our sides are, that our triangles are similar. So the triangles are similar, so we can use our rule. So let's find the side ratio. So the length of the side of the small triangle ABC is 4. What's the length of the side of the big triangle? ADE. 9. This is 4, this is 5, so the whole length here is 9. So the side ratio is 4 over 9. The area ratio? We just square that. 4 squared over 9 squared. 4 squared is 16 and 9 squared is 81. So their area ratio is going to be 16 over 81. And usually when you write a ratio, you're going to want to write it as a fraction.
Are you ever going to reduce or decrease? I know you can reduce.
Yeah, you could, if you can reduce, you can. You would reduce. So our area ratio is going to be 16 over 81. What if the problem asked us find the ratio of the perimeters? Of triangle ABC and triangle ADE. What would we do for that? So is perimeter a length ratio or an area ratio?
Pretty much like a length.
Well, perimeter is a length times is 3 times, yeah, sort of like a length times 3. Is the side ratio a length ratio? Yeah. So the perimeter ratio is a length ratio. It's going to be the same as the side ratio, because if we multiply the top and the bottom, if you think of an equilateral triangle, if you multiply the top by 3 and the bottom by 3, those 3's just cancel out. So any length ratio between similar figures is going to be the same as is going to be the same. So a side ratio, the perimeter ratio, a height ratio, any length ratio is the same. So it's the same as the side ratio. And that equals 4 over 9. So any length ratio between similar figures is going to be the same. So I know the ratio of the sides, the ratio of the perimeter is going to be 4 over 9, the ratio of the heights of the triangles will be 4 over 9, the ratio of the, whatever, the medians of the triangles is going to be 4 over 9, any length is going to be, ratio is going to be 4 over 9. Yeah.
So, what if we have like a new triangle where all the sides are not equal?
Doesn't matter. It doesn't matter. The perimeter ratio, the height ratio, any length ratio, as long as we know the two triangles are similar, is going to be exactly the same. Well, they have to be similar to use these rules. They have to be similar to use these rules. All right. What if we have an area ratio and we want to find the side ratio? So we know the area ratio. We find the side ratio, and by side ratio, any length ratio. Find the length ratio. Length ratio could be side, perimeter, any length, by taking the square root. So if we know the area ratio, to find the length ratio, we take the square root. Just like if we have, anytime we have something squared, and we want to undo the square, we take the square root. Same idea. So an example of that would be, we have the surface area ratio. Of two spheres is 144 over 169. And the problem says, what is the ratio of their radii? So surface area is an area. It's an area ratio. Radii is a radius, a length, an area, a volume. Radius is a length. So we want a length ratio. Now before we do that, we need to know our shapes are two spheres. Are two spheres similar?
Yep.
Can spheres ever not be similar? Can two... So our kind of everyday definition of similar was same shape, different size. Can two spheres ever be different shapes? Aren't spheres always just a ball? Yeah. So two spheres are always similar. Spheres are always similar. So we know we can use our rule. So our area ratio is 144 over 169. Our length ratio is the square root of 144 over the square root of 169. And if we plug that in our calculator, we get 12 over 13. So the ratio of their radii is the length, the ratio of the radii is going to be 12 over 13. So if we have the area ratio and we want a length ratio, we take the square root. So questions on that one? All right, so now we know how areas of similar figures are related. Let's talk about similar solids and volume. So we have two similar solids. And we're going to start the same way. And by length ratio, I mean a side, a circumference, a height. Any length of A over B, just like before. Those solids are going to have a volume ratio A cubed over B cubed. So to go from length to volume, we cube. And we can think of it just like we thought of our units. Length is inches, centimeters, meters, whatever. Volume is cubic inches, cubic meters, cubic, whatever our units are. So to go from length to volume, we cube. So our shortcut here is cube the length ratio to get our volume ratio. So that's our shortcut. To go from our length ratio to a volume ratio, we cube. And again, when we have similar solids, any length ratio that we compare is going to be the same. So if we know that, say, our two spheres have a ratio of radii of 1 to 3, the ratio of the circumference is going to be 1 to 3, the ratio of the diameter is going to be 1 to 3. Any length ratio is going to be the same. And to get the volume ratio, we just cube that. So questions on what that rule is telling us? Okay, let's look at an example of that. So we have two spheres. With radius 5 centimeters and 7 centimeters. We want to find the volume ratio. So first off, we're going to make a ratio of the lengths. So our length ratio is, how do we want to write our length ratio? 5 over 7. So our volume ratio is going to be 5 cubed over 7 cubed. And I plug that in my calculator, and that's 125 over 243. So our volume ratio is going to be 145 over 243. So questions on that example? Go from length ratio to volume ratio, we cube. So what if we're given the volume ratio and we want the length ratio? What if we're going the other direction? Cube root. If we have the volume ratio, yes.
On the last problem,
Uh-huh.
7 cubed is 342.
Did I write my digits in the wrong order? 2, I put a 2. Thank you. Yes, I have it written down correctly here. I just didn't write it down correctly there. All right. If we have the volume ratio, to get the length ratio, and again, length is any length that we're talking about, radius, diameter, height, perimeter, any length ratio, use the cube root. So that's this thing. So just like we undo a square with a square root, we undo a cube with a cube root. So we go backwards from a volume to a length, we use a cube root. So let's look at an example of that. So we have the ratio of the volumes of two similar prisms. is 64 over 125. We want to find the ratio of their heights. So we have a volume ratio. Is a height a length or an area or a volume? Height, length, area, or volume? Length. Height is a length. So we want to find a length ratio. So our volume ratio is 64 over 125. Our length ratio is the cube root of 64 over the cube root of 125. Cube root of 64 is 4. Cube root of 125 is 5. And we plug that into our calculators to find it if you don't remember those cube roots. So our height ratio is going to be 4 to 5. The ratio of the side lengths would be 4 to 5. The ratio of the perimeter of the bases would be 4 to 5. Any length ratio is going to be 4 to 5 between those two similar prisms. And we found that by taking the cube root of the volume ratio. Any questions on that? So pretty straightforward rules. Go from length to area, square. Go from area to length, square root. Go from length to volume, cube. Go from volume to length, cube root. All right, and we didn't have homework last night, so let me give you today's homework. The homework that's up on the sideboard is not the correct homework, so let me give you the correct homework. There you go.